Alright, we're back for another round with this molecule. So, in a previous video we determined that the three carbons in this molecule are all configured R. If you haven't watched that video yet, this is really kind of a part 2. It's actually a part 3. If you haven't watched that video yet where we figure out R, that they're all R, go back and watch it now. And then come back to this one. Okay, so the name is shown down here below: 3R chloro, 4R methyl, 1R cyclohexanol. So let's, again, in that earlier video I had a mirror plane and I drew, so I drew this, I drew the enantiomer. And this takes some getting used to, where you can draw that mirror plane and then reflect it. Okay, so that would be the enantiomer. They're non-superimposable. And in fact, what you'll find is, go back to that earlier video, and if you assign priorities, so for example, on this carbon, the hydrogen is 4, it's away. The carbon with the chlorine is high, that's 2, that's 3, so you go 1 to 2 to 3, right? That's a counterclockwise, no, sorry, that's a clockwise circle, so it's R. When we reflect the molecule, and it doesn't turn, it reflects. Again, the priorities basically stay the same, 1, 2, and 3, but now you've reflected the clockwise circle, and it's a counterclockwise circle. That's going to make this an S carbon. And if you do that for all of these, you'll find that when you do this mirror reflection, all R's should turn to S, and all S's should turn to R's. Okay, so the name of the enantiomer, let's connect these. So this is that guy. You can name the enantiomer easily. Same name, just change the R's to S's and the S's to R's. Running out of board. Okay, so it's exactly the same name. The enantiomer of a molecule, if you can name a molecule, you can name the enantiomer easily. Right, so we named this molecule in the previous video. Well, if I know that this molecule is the enantiomer, then it's exactly the same name. I just change R to S, R to S, R to S. If I had had an S in there, I would change that to R. Right, when we do a mirror reflection, every chiral carbon will invert. Okay, I'm going to erase the names now. Sorry, I'm going to connect the names. So this name goes there. All right, that's the bottom is the enantiomer, the top is the original molecule. Okay, I'm going to erase that now. So now I'm going to show you another way to draw an enantiomer. Like I said, R changes to S, S changes to R. So instead of drawing the mirror image, you can keep the skeleton the same, the two-dimensional skeleton the same, and simply invert each substituent. So this methyl is out, make it go back. The chlorine is back, make it come out. OH is back, make it come out. And what you'll find now your 1 to 2 to 3 circle, which is clockwise based on the priority, it's still going to be clockwise based on priority. That's going to be 1, that's going to be 2, that's going to be 3. But now the hydrogen is sticking out at you, and so you have to take the reverse. So again, this winds up with S, S, and S. And these two structures then are identical. Pause it if you don't believe that. Pause it and draw what you would get if you take this structure and turn it over. Okay? So if I take this molecule and I turn it over, so the 6-membered ring stays the same. We spin it, the methyl comes around at you, the OH goes around behind the board, the chlorine comes to this side of the molecule from the right to the left and back. It's exactly that structure. So there are two ways. Hang on a sec. There are two ways to draw enantiomers. You can draw a mirror image, or you can simply invert each stereocenter. You have to invert every chiral carbon. If you leave it, like what happens if you just do one? Okay, so let's invert the methyl, and let's invert the chloro, and let's leave the OH the same. This is now not an enantiomer or a mirror image of any of these structures, right? Look at this. The methyl and the OH are trans in the original structure. The methyl and the OH are cis in this structure I've drawn down here. So if we go through and do the configurations, this would be SS and R. So this molecule, what is the relationship of this molecule with the original structure? Think about it, pause if you want. All right, this structure I've drawn where I change two of the chiral centers but leave one alone, this is a diastereomer to the original. And so anytime you have multiple chiral centers, if you change some but not all, the molecule will be a diastereomer. All right, we'll come back and talk about how many stereoisomers there can be for this molecule in another video.